Hi everyone, today at the seminar we are hosting Adam Karczmarz. Adam, please start.
Okay, so hello everyone. Okay. So in this talk, this is a joint work with Piotr Sękowski. So in this talk, we focus on real-weighted directed graphs. We will denote by n the number of vertices and by m the number of edges. So I will be talking about computing shortest paths between all pairs of vertices of G. So this is a very well-studied and fundamental problem. It is conjectured that one cannot obtain a truly subcubic algorithm for this problem for all graph densities. However, for sparse graphs, we can get quite close to the optimal quadratic bound. Namely, we can get roughly nm time. So recall that in order to achieve that, we first reduce the problem to the non-negatively weighted case using a simple Bellman-Ford run, and then we just run Dijkstra from each possible source. So Dijkstra runs in nearly linear time. And this is also often called Johnson's algorithm. And in this talk, we study the APSP problem in the parallel setting. So we will use a simplified parallel computation model in which a parallel algorithm is characterized by two quantities. So first, the work of a parallel algorithm is the total number of primitive operations performed. So for sequential algorithms, this is also called time. And second, we have the depth defined as the longest chain of sequential dependencies between these operations. So by so-called Brandt's law, the depth is basically the limit on how fast you can run your parallel algorithm if you have sufficiently many processors. So throughout, when talking about parallel algorithms, we always use the O tilde. We always use the O tilde notation instead of the standard big O notation. So this allows us to not care about some low-level details such as what is the shared memory access model, because there exist general reductions between all these different models with just polylogarithmic overhead. Moreover, this allows us to say that every time we compute a minimum of n values without any dependencies between them, we can do it using nearly linear work and almost constant depth. So if you forgot how this is done, then you basically need to build a binary tree on top of your values to make the depth logarithmic. And because we don't care about the memory model, some of these values may even refer to the same memory cell, like this. So we need one more definition. So suppose T of n is the best known bound on the time needed to solve some problem using a sequential algorithm. Then a parallel algorithm for this problem is called nearly work efficient if it has work only polylogarithmic factors away from T of n. So by this definition, any state-of-the-art sequential algorithm is obviously work efficient. However, in general, it can have depth equal to the sequential time. However, it is not always that bad, and often we have some natural parallelism in the algorithms we study. So, for example, consider Johnson's algorithm. Then we will see in a moment that its first step, namely Bellman-Ford, has depth linear in n, and moreover, all the subsequent Dijkstra runs are independent, so the depth trivially reduces to roughly n. Dijkstra's depth can be reduced even further to n with some tricks. So basically, the baseline nearly work-efficient parallel APSP algorithm has depth linear in n. So of course, ideally, we would like to have a nearly work-efficient algorithm with constant depth. However, this is not always an easy task to achieve, and many of the known constant depth algorithms are very far from being work-efficient.
If I may ask, I would like to understand better how this depth works. So is it easy to show that the depth for Bellman-Ford is O of n?
Yes, it's easy. I will go through it in a moment. So it's
okay. Yeah. So sorry.
I will cover it in my preliminaries. In our paper, we show a deterministic parallel APSP algorithm that is nearly work efficient and has depth no more than roughly n to 1/3. And our algorithm should be compared with the following most closely related results. So first of all, to the best of our knowledge, no other non-trivial nearly work efficient parallel APSP algorithm has been described. So the baseline is Johnson's in terms of nearly work efficient algorithms. However, you can easily achieve polylogarithmic depth with the folklore matrix squaring approach. So we'll go through that in a moment as well. Ullman and Yanakakis, among some other results, show that for work-efficient transitive closure, root n depth is possible. And finally, Brinkman et al. Got the same depth as we do, but for SSSP and using randomization. So our algorithm most closely resembles this last result, but we are a bit smarter here and solve a more general problem without randomization. Okay, so the plan for the rest of the talk is as follows. So first, we will introduce some notation, recall some basic shortest paths algorithms, and make sure we know how they can be implemented in parallel. Next, we'll obtain the claimed bounds for parallel APSP using randomization. And afterwards, we will de-randomize the algorithm and, by the way, show a nearly optimal deterministic algorithm for computing a shortest negative cycle. And finally, we will show some applications for planar graph algorithms. Okay, so let this thing highlighted in blue denote the, sorry, can you? I would like this top bar to disappear, but I don't know how to do it. Okay, so let this thing highlighted in blue denote the...
Something like F11 or something like this.
Yes, I did that, but it's there.
Okay, maybe click somewhere.
No, doesn't work.
Okay.
Okay, so let this thing highlighted in blue denote the minimum weight of an U to V path in G that consists of at most k edges. We also call these edges hops. And we also call this notion, this blue thing, the length of the shortest hop, k-hop constraint path. Also, the mean plus product of two real matrices is like usual matrix multiplication, but we replace plus with mean and times with plus. This is pretty standard. It is well known that computing a mean plus product is kind of an operation that is equivalent to APSP, so it likely requires cubic time as well. Now let A be the weighted adjacency matrix of G, so a matrix with 0 if U and V, for element UV if U and V are equal, and otherwise this element should contain the weight of the edge UV. And it's easy to show that if we take the kth power of A using the weighted adjacency matrix A, if we take its kth power, then basically it represents exactly the hop constraint shortest paths as defined in the top here. So now, given that, it is easy to get a parallel APSP algorithm with constant depth and cubic work. So this is the folklore algorithm. Namely, it is enough to compute A to the power n-1 using mean plus product because the shortest path has less than n hops, and unless there are some negative cycles. So using repeated squaring, we use log n mean plus products. Sorry, and each mean plus product is basically n squared independent n-way computation of minima, so it has nearly constant depth. And that's why the depth of the algorithm is also nearly constant. However, obviously, this algorithm is work efficient only for very dense graphs. Now, let us recall what was the Bellman-Ford algorithm. So basically, it is an algorithm for computing single source shortest paths in presence of negative weights. It can also detect a negative cycle if one exists, but we will not go into that. Bellman-Ford goes like this. So given a source S, the algorithm maintains a vector of distance labels, and initially all these labels are infinite except of the label of the source S, which is set to 0. And then a number of Bellman-Ford steps are performed. So a Bellman-Ford step relaxes all edges in arbitrary order. So to relax an edge UV means to try to improve the best path to V by going through UV as the last edge. So it is easy to prove that, first of all, D of V is always equal to the length of some S to V path unless it's infinite. And moreover, after K Bellman-Ford steps, the distance label of V is no more than the length of the shortest K-hop constraint S to V path. So if G has no negative cycles, we will have that after n Bellman-Ford steps, the labels will correspond to distances from S. So that's the textbook variant of Bellman-Ford. But for simplicity, we will use a variant of Bellman-Ford that converges to the answer slightly slower. So so it's like this. So in a single phase, it just instead of relaxing all edges one by one, it just computes for each vertex V and the minimum over all incoming edges of V of the minimum through all the incoming edges of V of the corresponding label plus the edge weight. And then after K steps, the labels represent exactly the K-hop constraint distances. So for this variant, it is clear that the operations in a single phase are independent because we just compute some minima independently for each vertex. And the dependencies arise only between the subsequent steps. So it is easy to see that now performing K Bellman-Ford steps like this can be done using order MK work and using K depth. So are you okay now with the depth of Bellman-Ford? Okay.
Yes.
Okay, so now we are ready to give a basic randomized version of our algorithm. And the main trick in this algorithm is not new. So I believe it should be traced back to Bernstein's nearly optimal decremental approximate APSP algorithm that works for positive integer weights. And basically, we noticed that in the static sequential setting, this algorithm can be adapted to compute APSP for real weights. That's one thing. And what is more important, the algorithm runs in almost NM polylog n time without ever running Dijkstra. So it has some potential to be parallelized. And another nice thing is that it does not require an explicit step that reduces the problem to the non-negative case, like in Johnson's algorithm. Okay, so let us first assume that G has no negative cycles. So now let's define the key concept in this talk. And so we call a set H an H-hub set of G if for any pair of vertices UV from the vertex set, some H-hub shortest path between these two vertices goes through a vertex of a hub set. If, of course, only if such a path exists. So this simple example, we have just two vertices and three different shortest paths between the two vertices U and V. And with this definition, the hub set is only required to hit one of these two. So okay, so the edges without labels are assumed to have weight 1. And in this example, the hub set is only required to hit one of those two 3-hop paths. So we do not care about shortest paths with not too many hops. And it turns out that for any h, we can basically compute a small h-hub set that is correct with high probability by just taking a random subset of v of size n over h log n. So we do not even care what our graph looks like. We just sample some random subset and we are done. And it's guaranteed to be a good hub set, h-hub set. So most algorithms that I am aware of that use hub sets as defined as before. So they usually pick a hub set for some single chosen value of h, and then based on it give some trade-off algorithm. So this, for example, happens in the mentioned parallel algorithms of Ullman and Yanakakis, and the other one of Brinkman et al. And the idea of Bernstein's algorithm is to have a hierarchy of h-hub sets instead. So for all, we have a hub set for all possible magnitude of h. More concretely, we'll use h-hub sets for h equal to all powers of 2 up to n. So the 2 to the i, hub set, for example, if we sample it, it will have size n over 2 to the I log n. And in the following, when saying distances between A and B, we actually mean distances between all pairs of vertices U, V, where U is in A and V is in B, or the other way around. So now the key lemma is as follows. So suppose we have suppose the distances between the 2 to the k plus 1 hub set and V are already known. Then we show that the distances between the 2 to the k hub set and V can be computed in time the size of the hub set, times 2 to the k times m, which given that the size of a hub set is n over 2 to the k log n, this is nm log n. So given that, the algorithm will be as follows. So we start with h to the 2 to the l hub set, and this is an empty set, so we don't have to compute anything. And then we apply the lemma for subsequent decreasing values of k. And after log n such applications, we'll end up with all pairs distances, since the one hub set h1 equals the whole vertex set. So the total time will be order nm log squared n. So now let us prove this lemma. So once again, recall our goal is to given distances between a 2h hub set and V, we want to lift these distances to distances between an h hub set and V. Okay, so how to do it? So let S be some h hub, and let us define GHS to be a graph G, but with a shortcut edge from S to each V from the 2h hub set added. And the weight of the shortcut equals the distance between S and V in G. So recall that we already have that distance as our input. So in other words, GHS is just the graph G with some order n auxiliary edges added. So we will prove that 2h plus 1 hop constraint distances from S in this augmented graph are the same as distances from S in the original graph G. So how will this help us achieve our goal? The goal that is in the top. So for each starting vertex, so for each hub S from the H hub set, we run 2h plus 1 Bell-Mulford steps on the graph GHS, and this will take order HM time. And yes, and by the lemma, this will give us the shortest paths from all the hubs from the H hub set. And to all hubs, since the size of the hub set is n over H log n, to all hubs, this time will be the size of the hub set times HM, which will be nm log n. So this will give us the distances between the hub set and V, and to produce the other distances, like from V to the hub set, we just proceed symmetrically. Okay, so let us sorry. So let us now prove this fact. First of all, we want to establish that the distances in G and the augmented graph GHS are the same. So that's claim 1. So since the G is a subgraph of GHS, a distance in GHS cannot be larger than that in G. So, however, the shortcut edges also do not improve upon paths in G. The shortcut edges that we added also do not improve upon paths in G, since their weights correspond precisely to distances in G. So that's claim 1. Now we want to see that 2H plus 1 hop constraint paths in GHS are not shorter than shortest paths in G. But this is easy by claim 1, because a hop constraint path cannot be shorter than a non-constrained path whose minimum length equals the shortest path in G. So to prove the lemma, it is sufficient to prove the reverse inequality, namely that 2H plus 1 hop constraint paths in GHS are no worse than the paths in G. So to this end, let K be a minimum hop length of a shortest U to V path in G. So if K is small, if it's not more than 2H, then we are okay, since basically the 2H plus 1, the K hop constraint paths are preserved in what we compute. So the 2H plus 1 hop constraint paths already capture this case. So suppose that the K is more than 2H, and let us take some K hop shortest path P from U to V, like this. And now let us consider its 2H hop suffix Y to T. So this suffix is also a shortest, is of course a shortest Y to T path. So by the definition of a hub set, there surely exists some blue Y to T 2H hop shortest path that goes through a vertex Z from the 2H hub set. But recall that we have a single hop shortcut from S to that hub Z, to that hub Z, which certifies the existence of this green path with no more than 2H plus 1 hops, and length exactly the same as the original, as the S to T shortest path that we started with. Yes, so that proves claim 3. So that's basically it for the alternative sequential algorithm. So now let us consider its parallel implementation. So first of all, we have log n lifting steps, and the kth of them has order n over 2 to the k independent Bell-Mumford runs, each with order 2 to the k steps. So the work is nm and the depth is 2 to the k. So as a result, the total depth of this algorithm equals, basically is dominated by the depth of the last alpha step, which is n. So the depth is not better than the depth of Johnson at this point, but it is now easy to guess how to improve the depth. So let D be some desired depth that we want to achieve. And the idea is to replace the steps with high depth. So the sum of the final steps, which all operate on small hub sets, with the algorithm for dense graphs. which, as you may recall, had polylogarithmic depth in all cases. So to see that this is indeed possible, we need two simple observations. So first, for step capital D, all we need is distances between the 2 to the D subset and 2 to the D plus 1 subset to produce the shortcut edges. So to see that, simply recall the definition. So we did not actually use all the input distances. We only wanted to use distances between our current subset and the previous subset. And moreover, since a 2 to the D subset is a 2 to the D plus 1 subset as well, but it's possibly larger, we can make these subsets equal. And that being said, all we need to avoid performing the high depth steps is basically distances between the D hubs in G. So to get them, consider the graph GD, a complete graph on the D hub set, which encodes the D plus 1 hop constraint distances between the D hubs in G. So one can inductively prove that the distances in this dense graph GD and G are equal for the D hubs. So we are going to skip the proof right now, but it's not that hard. And given that, the improved algorithm is now as follows. So we first construct this dense graph GD using Bellman-Ford. So this takes only NM work again and D depth. And next we compute APSP on GD using the repeated squaring algorithm. So it takes N over D cube work and constant depth. And then we resume the lifting steps starting at K equal to capital D for all smaller values of K. And this takes, again, NM work and roughly D depth. So this proves that we can get a trade-off of NM plus N over D cube work and D depth for any parameter D. So to minimize the depth and still be nearly work efficient, we pick D like this. So N squared over M to 1 over 3. Yes, so that's the randomized algorithm. And now let us talk how to de-randomize this algorithm. So observe that the only place we used randomization was sampling a hierarchy of subsets. It turns out there exist some other results on sparse graphs that need randomization only for this particular reason. So, for example, Orlin et al. Used the subsets, the hierarchy of subsets, to show a nearly optimal sequential algorithm for finding a shortest in terms of hops negative cycle, again in a real weighted directed graph. Again, one cannot improve upon that if one believes in the APSP conjecture. So we show that for any parameter D, there exists a deterministic algorithm with NM work and D depth that either finds a negative cycle with no more than D edges, or otherwise computes a collection of 2 to the I subsets for all powers of 2 up to D. So the subsets are of roughly the same sizes as the sampled subsets. Okay, so, and in order to deal with negative cycles, we need to slightly strengthen our definition of a subset. So first of all, let us call an U to V H-hop path minimal if it is shortest among the H-hop constrained paths, and all paths with less hops are longer than this. So then we would like our stronger H-hop sets to hit some minimal H-hop path for all pairs UV if one exists. So the stronger H-hop set does not only hit H-hop shortest paths, but also shortest h-hop constraint paths, unless they are no better than paths with even less hops. Then we do not care about hitting them. So the parallel APSP algorithm that we showed also works with this definition of a hub set, and all the proofs go through without a change. So to proceed, we will first need a simple deterministic algorithm for computing hitting sets. So recall that a subset X of V is a hitting set of a family of subsets S1 to Sk of V if X has a non-empty intersection with all the hub sets of that family. And now if all these sets Si have the same size H, then one can compute a hitting set of size n over H log K deterministically using a greedy algorithm. And the algorithm runs in linear time. So let us go through this algorithm because it is very simple. So suppose at some point there are still L sets to be hit, and then some best element V that hits the most of the remaining sets. It surely hits at least an H over n fraction of the remaining sets. So taking that best V basically multiplies the quantity L by a factor 1 minus H over n. So after n over H steps, the quantity L gets reduced by a constant factor. So this can clearly happen no more than order log n times. And luckily, this greedy algorithm can be parallelized very well if we do not mind increasing the size of the hub set. If we do not mind increasing the size of the hitting set produced by only a constant factor, which we, of course, don't mind. So now, how can we use that? So the general idea is the same as in the APSP algorithm. So given an H hub set, we want to lift it to a 2H hub set of size n over n log n. And we want to spend only, roughly nm work and H depth on this. So in order to do that, we need one additional requirement, that there is no negative cycle with at most 8 edges. So the procedure will also be able to identify a shortest negative cycle unless it has more than 2 edges. Okay, so given that, we proceed in the opposite direction compared to the APSP algorithm. Namely, we start with H1 equal to the whole vertex set. So it's trivial to compute that, and apply the above lifting idea for all the subsequent powers of 2. Now let me explain how this lifting is performed. So we showed that it is enough to, in order to get the H hub, in order to get a 2H hub set, it is enough to hit all the H hub minimal paths from the H hubs, from the hubs of the H hub set. So to prove this, consider a 2H hop minimal path P between some 2 vertices S and T, and consider its H hop prefix. So since the whole path is minimal, so is its prefix from S to W. And by the definition of an H hub set, some minimal S to W path is hit by a vertex Y from the H hub set. So now if you consider this blue path, now consider this blue path and its H hop segment starting at the vertex Y. Y was here. So it is also a minimal H hop path by the minimality of the path P, the original path P. And so if we hit some minimal H hop Y to V path, like the green one, we also hit this whole orange 2H hop minimal S to T path. So basically, this proves that the computed heating set, the computed heating set is a desired 2H hub set of G. Okay, so the algorithm is now as follows. So we first compute the minimal H hop paths from all the H hubs, those that exist. This takes roughly nm work and H depth using Bellman-Ford. And now, since there are no negative cycles with H or less hops, all these paths are guaranteed to be simple. So we can compute their heating set of size n over H log n using nm work and only polylogarithmic depth using the greedy algorithm. Finally, how do we compute a shortest negative cycle with at most 2H edges if there is no negative cycle with at most H edges? So consider a shortest negative cycle with more than H but no more than 2H edges. And consider some H hop segment of this cycle, here shown in red, and it has to be an H hop minimal path, as otherwise we could replace it with a path with not larger weight but smaller number of hops, and it would give us a shorter negative cycle, which we assumed it do not exist. And again, since we hit all the minimal H hop paths, some alternative H hop segment of the same weight has to go through a vertex of the H hop set. This is the vertex. So now this blue cycle is also a shortest negative cycle. So basically, this proves that in order to find a shortest negative cycle, it's enough to compute shortest at most 2H hop constrained paths from all these hubs from the H hub set. Yeah, we want to compute the hop constrained paths for all the possible numbers of hops, but this number is bounded by 2 to the H. And from this, we can find the minimum hop negative path from a hub to itself. That would give us, if we minimize this through all the H hubs, this will give us the shortest negative cycle in this case. And again, this takes nm work and order H depth. Okay, so now the final part, let us show some planar graph applications of our APSP algorithm. So almost immediately we get nearly work optimal algorithms for problems concerning shortest paths, matchings, and flows. For all of them, we get roughly n to 1 over 6 depth. And for all of these nearly optimal, for all of these listed problems, nearly optimal sequential algorithms have been known for a long time. However, even though parallel algorithms for planar graphs, it does not seem to be a very popular research area. Earlier work only implies algorithms with either n to 3 halves work and polylogarithmic depth, or the other trade-off is nearly linear work and root n depth. And using known techniques, the improved parallel negative cycle detection algorithm can also be used to get a faster, strongly polynomial time for computing a minimum cost to time ratio cycle in a planar graph. So in particular, we get n to 9 over 8 time algorithm for the real weighted case. So all of these applications are obtained as follows. So a very common abstract building block in planar graph algorithms is like this. So suppose we are given a plane graph G with a distinguished set of P boundary vertices, all lying on a single face of G. So think of B as much smaller than n. We need to compute all pairs shortest paths between these boundary vertices. We also call a boundary. We also call a graph on a complete graph on the boundary vertices representing those distances, a dense distance graph, DDG for short. So Klein showed that one can solve this. One can compute this all shortest paths between boundary vertices in time roughly linear in n and p squared. So the output has size p squared. So of course we need to add that term. But sometimes, in addition to the graph G itself, we are given its partition into G1 and G2, where the common vertices of the parts form a path like this. And suppose there are around B of those vertices on the path as well. So now assume that we already know the distances between the boundary vertices of G1 and independently separately the boundary vertices, the APSP between the boundary vertices of G2. So in other words, we are given dense distance graphs of both G1 and G2. Then the DDG of the entire G can be computed by running any APSP algorithm on the union of the respective DDGs of G1 and G2. So using the Folklore algorithm, the Folklore parallel algorithm, in this case, DDG of G can be computed based of DDG of G1 and DDGs of G1 and G2, naively using P-cube work and polylogarithmic depth. There also exists a very fast implementation of Dijkstra's algorithm on DDGs, and this implies a B squared work and B depth algorithm. So now we show that using some known tricks, our algorithm can be implemented on DDGs to run in B squared work and only roughly B2/3 depth. So this is possible since a dense distance graph has a very special structure. Namely, it is composed of two so-called staircase Monge matrices. Now consider a Bellman-Ford step. So relaxing all the edges of a dense distance graph can be done via a constant number of computations of column minima in a staircase Monge matrix. So luckily, we know very efficient algorithms for this task. So for an n by n staircase Monge matrix, we can compute the column minima either deterministically in n alpha n time, which is a very old result, or we can do it in linear expected time, which is a very fresh result, or we can also do it very efficiently in parallel. So nearly optimally. So this implies that each Bellman-Ford step takes n work and polylogarithmic depth in our case. What is also perhaps surprising is that a variant of our APSP algorithm can also be used to improve the sequential implementation of this DDG APSP computation. So far, the fastest way to do that was to use these B-runs of Fakharompo's and Rao's Dijkstra implementation on DDGs, and this gave us B squared log squared B time. But let us recall what was what was the sequential complexity of our parallel algorithm. Namely, it was like this: for any D, we had log D lifting steps, and each had cost equal to n log n times the Bellman-Ford steps cost. And moreover, we run dense APSP algorithm on the D-hub set. So as a result, the running time was like this, and yes, this red term, it corresponds to computing APSP between the D-hubs. But we can also compute APSP between D-hubs by just running Dijkstra from each of them. And then we get this running time. where here the BF is the cost of a Bellman-Ford step, and capital D is the cost of one Dijkstra computation. So since for dense distance graphs we have a very fast implementation of Dijkstra, we obtain by plugging in all these different bounds, we obtain this bound for this blue bound for any parameter D. So by choosing D equal to log squared of B, we obtain P squared log B log B times. So almost a single log factor less than what was known before. Okay. So that's it. That's all I've got for you. And to conclude, we gave a deterministic, nearly work-efficient parallel APSP algorithm with roughly n to 1/3 depth. We also showed some applications in planar graph algorithms, and also we de-randomized some of the known results. Some obvious open questions are as follows. So first, it would be nice to improve the depth even further. It's not clear what's the limit actually for nearly work-efficient algorithms. I am not aware of any conditional lower bounds. And this would be cool even for the easier problem of computing the transitive closure, even if we allow randomization. So that's it. Thank you.
So, I mean, I don't know that much about planar graphs, but about the first part, where you are running from shorter to longer hops, it kind of has a similar structure to Uritz-Fick's APSP.
Once more?
Uritz-Fick paper on all per shortest paths, where you are increasing by a constant factor the number of hops you learn the shortest paths by a matrix products, and earlier matrix products you are doing kind of in a smart way, but at one point you need to fall back to some brute force computation. And
okay, so from what I know, all these papers of Uritz-Fick, like they want to use matrix multiplication as much as possible, so they operate on dense graphs.
Yes, of course. But I mean, structurally, that you have a sequence of increase.
Yeah. I mean, it's not a new concept. It's used everywhere but the point is like, yeah, it's not. But actually, it's not something that is very much used in the static setting. Or it's that this concept of hubs is especially successful in dynamic graph algorithms. But what we do actually doesn't have any applications for static algorithms, because like the power of randomized hub sets for dynamic algorithms lies in the fact that they are good even in the future. So they can hit even the graphs that we do not know yet. Of course, if one assumes some kind of oblivious adversary or something like this.
I mean, the concept of hubs is, I think, mostly used in practice. I mean, not only just in dynamic algorithms. It's just used in practice.
Yeah, but then they are maybe not defined this way to hit long paths, but in practice you probably use some hubs that optimize your search time as much as possible.
Yes. I'm just trying to relate to those results, at least on some level. It's easier for me to relate to hubs than to Munch matrices.
Yeah.
Because for hubs I have intuitions. For Munch matrices, I just know that they are there. Graphs.
Yeah. So by the way, I was rather shocked when I saw this Munch matrices, like this word Monge, because I only encountered it in a very different context of the longest increasing subsequences. So is it like a standard tool in planar graphs that they are used, or not? Is it?
I think so. I think like most of the results about like processing those are about processing Monge matrices are kind of motivated by planar graph applications. That's what I believe, and only later people started to notice that basically you can use them also for text algorithms, because like the DP matrix of your problem is a planar graph. And
okay, yeah, I didn't know that, so that's a great insight. Good to know.
I don't know, so yeah.
Yeah, any connection to dynamic graphs actually? Because I encountered this in the setting of a window longest increasing subsequence problem. So this is kind of like you may think of it as a dynamic graph problem if you like construct some graph there. So have you seen?
Okay, so you are referring to longest increasing subsequence, not longest common subsequence. Yeah. Okay, so I do not know, and I do not know what's the connection about longest increasing subsequence and Monge matrices. I meant the connections to longest
to LCS
common subsequence.
Yeah. So I know that they are used also there, or maybe even primarily there. But
okay,
yeah. Sure. Okay.
I think maybe the most famous papers I saw is computing shortest paths that have at most k edges, something like that. And of course, and then distances are given as Monge matrix, and then you can do this very efficiently. It's something like n log n time, n log k time. But the matrix has to have a special structure, and this is then something that you can use. For instance, some DP, as Adam said, some DP problems have this kind of structure, or weights for your DP have these properties. So if, say, you want to compute some questions so that you collect at most k items, say, then you can use, then you can get very efficient DP solution running on in n log n as opposed to say nk. By using this kind of things.
So do you know some specific paper that does this? Like I didn't.
Yes. I can find it. I need maybe a couple of minutes, but I can find it.
Yeah. I'm not sure whether this is applicable here, but it's certainly interesting.
Yeah, it might not be directly applicable, but anyhow, I will find the paper. Okay, finding a minimum weight scaling path. Okay, let me just share the link here.
Okay, let me just stop the recording and then we can continue the discussion.
Sure.